Tonight the universe speaks in the smallest flashes, millisecond signals that cross deep space and arrive with delicate scars from plasma gravity and time. This is a calm journey through fast radio bursts, how they form, how they change along the way, and why their origins still stay just out of reach. If this kind of slow science storytelling helps, please like the video and subscribe to Space Dreams documentary. It supports more quiet explorations like this. Now the darkness opens, the first signal begins. A millisecond can be long enough for a cosmic message to arrive. It is also short enough to hide almost everything about its origin. A fast radio burst is shortened to FRB. It appears as a radio flash lasting about 1 millisecond. That span matches the blink of an eye. The path can still cross entire galaxies. In deep space, a pulse begins as an expanding wave front. It resembles a thin shell that sweeps outward. The leading edge is crisp at first. Then the shell meets uneven material. A haze of free electrons forms layers and gradients. The wavefront passes through those layers. The edge becomes slightly softened. The pulse that arrives keeps its central spike. It also gains a gentle trailing smear. This is the first quiet clue. A pulse that lasts 1 millisecond cannot come from a region larger than light can cross in that time. Light travels about 300 kilometers in 1 millisecond. That distance is similar to the span of a long mountain range. It is small compared with a planet. It is tiny compared with a star. The duration sets a ceiling on the size of the active region. The source is compact or the emission is tightly gated. A slow visual settles around that idea. A narrow ring of brightness expands across an otherwise empty field. The ring is not made of matter. It is a moving boundary of changing electric and magnetic fields. The ring crosses a patch of thin plasma. The plasma is not uniform. It thickens toward one side. The ring slows by an almost unnoticeable amount there. The ring does not stop. It arrives with its parts slightly out of step. That out-of-step arrival is called dispersion. Dispersion is a frequency-dependent delay caused by free electrons. The higher radio frequencies arrive first. The lower frequencies arrive later. The whole flash becomes a brief downward slide in time. The delay is often a fraction of a second. The delay is still enormous compared with the millisecond core. The contrast between those timescales becomes another clue. The burst is brief at the source. The route is long and complicated. A calm payoff follows from this. Dispersion counts electrons along the path. It does not count them one by one. It acts like fog thickness on a long road. A denser or longer road gives a larger delay. A clearer or shorter road gives a smaller delay. This is why an FRB can hint at distance. It hints at how much ionized material lies between origin and arrival. The hint is imperfect. It is still powerful. The scene shifts outward. A spiral arm holds thin clouds. It also holds clearer gaps. Between the clouds, gas is partly ionized. Around the arm, a faint halo adds more electrons. The burst crosses these regions as a single sharp event. Each layer adds a small delay. Each gradient adds a slight stretch. The final pulse is not only a point in time, it is a fingerprint of the medium. Another payoff rests inside that fingerprint. The delay is stronger at lower frequency in a predictable way. That predictability separates dispersion from many other effects. Random scattering can blur a pulse. Turbulence can add a tail. Those effects vary with frequency too. Their shapes differ. Dispersion draws a smooth curve in time. Scattering makes a one-sided smear. A pulse can carry both. The combination becomes a map of two kinds of structure. One is the total electron content along the route. The other is the fine-grained texture that bends paths into echoes. A slow anchor returns to texture. The wavefront crosses a region of turbulent plasma. Density there fluctuates like ripples within ripples. The pulse is no longer a perfect spike. It becomes a spike with a fading echo behind it. The echo is not a second burst. It is the same burst spread out. Multiple, slightly different paths arrive at slightly different times. The differences are tiny. They are still enough to round the pulse. The limit of intuition appears here quietly. The same observed shape can come from different arrangements of plasma. A long, gentle haze can mimic a shorter, dense patch. A thin, turbulent screen can mimic a thicker, mild turbulence. Without a direct view of the route, the medium is inferred indirectly. That inference relies on models. It relies on assumptions about typical electron densities. It relies on how turbulence behaves over many scales. The observation cannot resolve the route itself. It only resolves the final time profile of the pulse. A payoff sits inside that limitation. Even when the route is ambiguous, the millisecond core stays informative. If the core remains extremely sharp, the route cannot be strongly scattering. If the core is broadened, the route contains more small-scale structure. If the dispersion delay is large, the integrated electron content is large. These ideas fit together without strain. Duration hints at compact emission. Dispersion hints at ionized material. Scattering hints at turbulence. The scale shift becomes gentle and steady. The emission is confined to hundreds of kilometers or less. The journey spans thousands or millions of light years. Between those extremes, the signal crosses boundaries and gradients. It crosses halos and arms, then voids. It crosses pockets where plasma is clumped. It crosses lanes where plasma is smoother. The burst arrives as a short event. It also carries the memory of a vast route. A final visual anchor stabilizes the tone. The burst passes the edge of a faint bubble of ionized gas. The bubble has a shell with a sharper boundary. Inside, the density is lower. Outside, the density rises. The wavefront grazes the shell. The pulse gains a subtle kink in its delay. The kink is small. It suggests structure that cannot be seen directly. This is why the mystery remains calm and persistent. The burst is too brief to tell a long story by itself. The route is too complex to be known in detail. Yet timing carries clues that repeat. The next step is to follow how the pulse is stretched across frequencies. The path begins to reveal itself one layer at a time. A burst can feel instantaneous even when its colours arrive in order. That ordering stretched across time becomes one of the calmest ways to sense distance. At this distance, a radio pulse travels as a layered wavefront. Each layer carries a different frequency. The layers move together through emptiness. They begin to separate when free electrons appear. Free electrons are loose charges that drift in thin plasma. The pulse does not lose its identity there. It becomes slightly fanned out in time. The higher frequencies slide ahead. The lower frequencies lag behind. The result resembles a soft unrolling ribbon. The ribbon remains narrow. It is only widened by the peth. A single number holds the scale. A typical delay can be about 1 second. That is like waiting for a quiet heartbeat. The original flash still lasts about 1 millisecond. This contrast reveals a simple truth. The source event is compact. The travel medium is expansive. The medium leaves a timed imprint. A slow visual anchor settles into place. A long corridor of darkness contains faint layered mist. The mist is not uniform. It thickens into a gentle gradient. It thins into clearer bands. The burst enters as a thin, bright seam. The seam becomes a slightly curved streak. The curvature is smooth. It is a signature of dispersion. Dispersion is a frequency-dependent delay caused by free electrons. The curve steepens at the low-frequency end. It relaxes at the high-frequency end. The curve is not decoration. It is measurement in another form. The first small payoff arrives quietly. The amount of dispersion reflects how many free electrons sit along the route. More electrons create more delay. Fewer electrons create less delay. The count is integrated. It adds contributions from every region crossed. A galaxy halo adds some. A spiral arm adds more. A diffuse intergalactic bridge adds more still. The pulse becomes a tally mark without any visible map. The tally is incomplete. It is still useful. Another checkpoint appears. The same total delay can come from different arrangements. A short dense screen can match a long thin haze. The pulse does not announce where the electrons are. It only reveals that they exist along the line. This is where structure begins to matter. A gentle payoff follows from structure. If the dispersion is high, the route likely includes thick ionized regions. If the dispersion is modest, the route likely crosses more void. These are not certainties. They are direction signs. The story of the burst becomes a story of path choices. The visual corridor changes. The mist forms a layered shelf. A sharper boundary appears. The pulse crosses that boundary. The curved streak gains a small kink. The kink is subtle. It hints at a transition between plasma regimes. A halo edge can do this. A dense cloud boundary can do this. A filament can do this. The path leaves faint bends in timing. The second small payoff arrives. A smooth dispersion curve suggests a mostly uniform electron distribution. A jagged curve would suggest irregularities. The jaggedness is often too small to see directly. The concept still guides interpretation. The signal is a ruler made of time. It measures without touching. It measures without revealing the full room. The scale shifts outward. A millisecond event begins in a region no larger than a few hundred kilometers across. The path can span millions or billions of light years. The route threads through multiple layers. It passes a galaxy disk where gas density rises. It passes a halo where density falls with radius. It crosses intergalactic space where density is low. It may cross filaments where density rises again. Each part adds delay. Each part adds none of its own image. The pulse carries timing instead. The limit of observation sits here. The route cannot be directly resolved. The pulse is seen only as a final time profile. Even a perfect timing measurement cannot place electrons at specific distances. The inference depends on models of typical plasma density. It depends on assumptions about how halos and filaments contribute. It depends on a statistical picture of unseen structure. The pulse alone cannot break all degeneracies. This is not failure. This is a boundary of what indirect measurement can do. Another small payoff grows from accepting that boundary. Even without exact placement dispersion, sets a ceiling on how empty a route can be. It sets a floor on how much ionized matter must exist. This matters for cosmic inventory. Intergalactic space is not truly empty. It holds diffuse ionized gas. That gas is hard to see by other means. A fast burst makes it countable through time. The corridor visual widens. The mist becomes a faint sheet that drapes across a vast region. The sheet has ripples. The ripples are slow. They are large compared with the pulse. The pulse passes through. Its curved streak deepens slightly. The curve remains smooth. The curve becomes a quiet record of large-scale matter. Another checkpoint appears. Dispersion is not the only effect. Scattering can add a tail. Absorption can dim parts of the band. These can confuse interpretation. Still, dispersion has a distinct shape. Its timing follows a consistent law with frequency. That consistency makes it a reliable anchor. The burst becomes a probe of plasma rather than a simple flash. The pace remains calm. The next step moves from counting electrons to sensing texture. The time curve hints at bulk material. The pulse shape hints at small-scale turbulence. The transition ahead is gentle. It turns from smooth gradients to grainy structure without changing the quiet tone. A pulse can arrive clean and still carry a soft afterglow in time. That afterglow often comes from small-scale texture in the plasma, not from a longer event at the source. In that region between stars and galaxies, the path is rarely smooth. It holds drifting charge arranged in patches. It holds gradients that bend slightly. It holds tiny fluctuations that act like invisible pebbles in a current. The pulse begins as a thin wavefront. It expands like a shell. The shell meets a region where density changes from lane to lane. The leading edge stays sharp. A faint tail appears behind it. The tail fades slowly. It is not a second burst. It is one burst arriving by many nearby routes. Scattering is pulse spreading from many slightly different paths. Like a flashlight beam passing through frosted glass, the light stays bright yet loses a hard edge. The important detail is geometric. A path that is bent a little travels farther. Farther travel means later arrival. Many tiny bends create a whole fan of arrival times. A calm visual anchor forms. A wide dark gulf contains a thin curtain of charged mist. The curtain is not uniform. It has grain. It has clumps that look like pale knots. It has gaps like narrow windows. The wavefront crosses the curtain. The crossing leaves a faint wedge behind the main spike. The wedge is smooth at first. It becomes slightly ragged at its far end. That raggedness suggests structure smaller than the wave itself. A small payoff appears. The tail shape reveals not just how much plasma exists. It hints at how that plasma is arranged. A gentle long tail suggests many tiny deflections. A short tail suggests fewer. A tail that changes with frequency suggests a specific kind of texture. The pulse becomes a probe of granularity. This is different from dispersion. Dispersion is a smooth delay across frequencies. Scattering is a smear around the main time of arrival. Both can exist together. They answer different questions. Dispersion asks how many electrons are along the path. Scattering asks how rough the path is. Another checkpoint follows. The roughness comes from turbulence. Turbulence is irregular motion that makes density fluctuate over many scales. The fluctuations form a spectrum. Some are large and slow, some are small and quick. The small ones matter for scattering. They tilt the wavefront in tiny amounts. Each tilt changes the effective route length. The pulse is then built from many near copies of itself. Each copy is delayed by a slightly different amount. A single number sets the scale without strain. The tail can last about 10 milliseconds. That is like the time between two gentle raindrops. The core remains about 1 millisecond. The contrast explains why the tail is informative. The tail is not the event. The tail is the route. Another visual arrives with slow clarity. A filament of plasma stretches across emptiness. It is ribbon thin on the cosmic stage. It has a brighter spine. It has dimmer outer layers. Along its edge, the density flickers in patches. The wavefront meets the filament at a shallow angle. A sharp boundary is crossed. The pulse acquires a longer tail at once. The boundary behaves like a screen. It concentrates the scattering into one region. This is another quiet payoff. When scattering comes from a screen, the tail shape can be more predictable. The screen acts like a single place where paths split. When scattering is spread along the whole route, the tail can be smoother and more blended. The pulse shape carries this distinction. It can suggest whether roughness is localized or distributed. The story remains gentle. A signal would pass through halos and voids. A signal would brush past shells around old hot gas. A signal would cross diffuse bridges between galaxy groups. Each region has its own typical texture. A halo can be smoother in its outskirts. A spiral arm can be clumpier. A bridge can hold faint but extended irregularities. The pulse does not paint pictures of these regions. It only brings timing, yet timing can still narrow possibilities. Another payoff settles in. A burst with very little tail likely avoids strong turbulent screens. That favours a clearer line through emptier space. A burst with a heavy tail likely crosses a rougher zone. That favours denser environments or sharper boundaries. None of this proves the origin. It constrains the route. Constraints are a kind of progress. The scale shift continues softly. The millisecond core links to structures thousands of light years across. A tiny difference in route length creates a measurable delay. That delay can be many times the original width. The cosmos turns small, path differences into visible time differences. This is why scattering matters. It turns invisible texture into audible rhythm. The limit of observation arrives without tension. The pulse shape is a mixture of two unknowns. One unknown is the intrinsic duration at the source. The other unknown is the broadening from scattering. The final pulse cannot cleanly separate them without additional clues. Frequency behavior helps. A broader tail at lower frequency suggests scattering. A constant width across frequency suggests a source-dominated width. Even then, models intervene. The exact scaling depends on the turbulent spectrum. It depends on whether the scattering is in one screen or many. It depends on geometry that cannot be directly seen. The observation is indirect. It measures time. It does not measure the full three-dimensional distribution of plasma. This limitation does not erase what is learned. It sets a boundary for certainty. Another visual anchor refreshes the calm. A distant region holds a faint bubble of hot gas. Its edge is a curved wall. The wall has a thin, bright rim where density rises. Inside the bubble, the density is lower. Outside, it is higher and more irregular. The wavefront grazes the rim. The pulse develops a tail that fades in a smooth exponential way. The curve is gentle. It's like light lingering in a room after a lamp is switched off. The lingering is not stored light. It is delayed arrival along many bent routes. Another payoff follows from the curve shape. An exponential-like tail is a common outcome of many small random deflections. It suggests a scattering process that is statistically stable. It suggests that the medium acts like a random field, rather than a single sharp mirror. This does not identify the medium. It identifies the kind of process. The narrative remains grounded in physical detail. The wavefront is a moving boundary. The plasma has layers and gradients. The irregularities act as refractive bumps. The tail is the shadow of those bumps in time. The next step becomes natural. Once the path roughness is sensed, position becomes more constrained. Timing differences between routes can hint at direction. The transition ahead is soft. It shifts from pulse shape to pulse placement in the sky. A burst can be too brief to point back at its origin in any simple way. Position becomes possible when the same wavefront reaches separated locations at slightly different times. At this distance, a radio pulse is not a point that travels. It is a curved surface that expands. The surface is a moving boundary between before and after. When that boundary sweeps across space, it meets one place first. It meets another place a moment later. That stagger in arrival is small. It is still enough to carry direction. A calm visual anchor forms in darkness. A pale, spherical wavefront glides outward. It is a thin shell with a crisp leading rim. The rim crosses a sparse veil of dust. It also crosses a clearer gap. The shell keeps its curvature. The curvature is the key. A small payoff settles in. If the wavefront were perfectly flat, direction would be uncertain. Curvature makes timing differences meaningful. A curved front implies a distant origin. The farther the origin, the flatter the curve appears locally. The closer the origin, the more the curve bends across a given span. This turns arrival time into a geometric clue. The journey moves closer to the idea of baseline. Baseline is the separation between two sampling locations. With a longer baseline, the same direction produces a larger time offset. With a shorter baseline, the offset shrinks. The burst remains a millisecond event. The timing offset can be far smaller. A single number holds the scale without strain. An offset can be about 1 microsecond. That is like a mote of time inside a single blink. Such a small shift can still imply a vast angle on the sky. The reason is simple. Light travels about 300 meters in 1 microsecond. That distance is similar to the length of a long bridge span. A wavefront that arrives 1 microsecond earlier at one location has crossed that extra path length. The path difference is real. It is set by direction. Another visual arrives in slow detail. 2 dark rocky spires float in a cold nebular void. The wavefront rim touches the nearer spire first. A faint glow of scattering appears along its edge. A moment later the rim touches the farther spire. The glow repeats. Nothing is watching. The stagger simply exists in the geometry. A payoff follows. The difference in arrival time defines a cone of possible directions. Many directions can produce the same time offset. They form a ring on the sky. With only 2 locations, the origin lies somewhere along that ring. A third location breaks the ring into smaller arcs. A fourth can shrink the arc further. The localization is not a point at first. It is a narrowing region. This feels like an ocean swell reaching islands. The same swell crest arrives at one island first. It arrives at another island next. The timing tells which way the swell is travelling. The islands do not need to know the ocean's centre. The crest carries the answer in its order. Another checkpoint appears. The wavefront is not a perfect sphere in practice. The medium bends it. Dispersion delays parts of the band. Scattering adds faint tails. These effects do not remove direction. They complicate timing. A burst that is clean in one band can be smeared in another. The sharpest part of the pulse becomes the best marker. The marker must be chosen carefully. A small payoff settles in. The most reliable timing feature is often the steep leading edge. Tails can wander with scattering. The edge is less ambiguous. The wavefront edge is a physical boundary. It arrives once. It does not linger. A slow, visual anchor changes scale. A broad filament of plasma hangs between galaxy groups. It has a brighter spine. It has dimmer outer layers. The wavefront crosses it. The rim that was smooth becomes slightly wrinkled. The wrinkles are gentle. They shift the time of the edge by tiny amounts. The origin direction can still be inferred. The inference now includes an uncertainty budget. The budget is shaped by the medium. Another payoff appears. Localizing an FRB is not only geometry. It is also a discipline of separating path effects from direction effects. If the medium delays one path more than another, it can mimic a change in direction. This is why multiple widely separated sampling points matter. Medium distortions differ across space. Direction is shared. When enough points agree on the same direction, path distortions are averaged down. The scale shift becomes quiet and steady. A microsecond offset is a short time. The implied distance to the source can be billions of years in light travel. A tiny offset on a small baseline can map to a broad arc across the sky. A larger baseline can shrink that arc. The shrinking is not dramatic, it is gradual. The process feels like tightening a loose ribbon into a thin thread. Another visual arrives. A wide arc of faint glow curves across a star field. It is the locus of possible origins. With another timing constraint, the arc becomes a smaller segment. With another, it becomes a compact patch. The patch is still not a pinpoint. It is a place where the wavefront fits best. The limit of observation appears here softly and specifically. Timing cannot be infinitely precise. The pulse has finite width. Scattering blurs the edge. Dispersion curves can be corrected only to a point. Even if the true edge is sharp, the observed edge is softened. The uncertainty in timing becomes an uncertainty in angle. Over cosmic distances, a small timing error becomes a large patch on the sky. The geometry is unforgiving. Another limit follows. The wavefront can be distorted by plasma structures near the source. A nearby screen can add an extra delay that depends on direction. That delay can masquerade as a different origin position. Without independent knowledge of that screen localization carries systematic uncertainty. This is the boundary of indirect inference. The result is a map with blurred borders rather than a single coordinate. Another small payoff rests inside that boundary. Even a blurred location is enough to connect the burst to an environment class. A location near a dense disk suggests one kind of path. A location in a halo suggests another. A location aligned with a filament suggests another. The burst begins to be placed within large-scale structure. This is progress that does not demand perfection. The imagery slows again. A dark lane of dust cuts across a faint glow of gas. The wavefront rim slides along the lane. The timing constraints narrow the origin to one side of the lane. The lane becomes a visual divider. The burst is no longer everywhere. It is somewhere. Another payoff follows. Once a burst is localized, its dispersion can be reinterpreted. Some of the delay can be assigned to the host region, some can be assigned to the intergalactic path, some can be assigned to the local surroundings. Localization turns one number into a layered story. It does not solve the engine, it clarifies the route. The gentle transition begins. Some bursts return more than once. Returns allow repeated constraints. Repetition can tighten location and separate medium effects from source behavior with calm persistence. Some bursts return without warning, as if the cosmos briefly reuses the same doorway. Repetition narrows uncertainty because the path can be tested again and again under nearly the same sky. At this distance, a repeating fast radio burst is not a single event. It is a sequence of short releases separated by quiet intervals. Each release still lasts about 1 millisecond. Each release still crosses the same broad intergalactic route. The differences between repeats become the new signal. A calm visual anchor forms in a dark field. A thin, luminous seam appears. It fades. The seam returns nearby, not identical but familiar. Between returns, a faint ribbon of plasma drifts across the line of sight. The ribbon has a layered edge. One side is denser, the other side is thinner. The seam crosses that edge each time. The leading rim remains sharp. The tail changes slightly. The changing tail is the first clue. The path is not frozen, it evolves. The burst acts like a bell struck more than once. The bell is not metal, it is the medium. The strike reveals the bell's changing tone. The small payoff arrives early. If two bursts from the same source show different scattering tails, the change likely comes from the route near the source. The intergalactic part changes slowly over ages. The nearby environment can change over days or months. This separates scales without effort. It places the most active distortions close to where the burst begins. The journey moves into a second concept. Some repeats show a shifting dispersion measure. The shift can be small, it still matters. Dispersion measure is the integrated electron delay along the path. Like a long hallway where fog thickens and thins, the delay changes if the fog near the start changes. A dense knot moving across the line can add extra delay. When the knot moves away, the delay relaxes. Another visual anchor arrives with steady pacing. A hollow cavity of ionized gas surrounds a compact region. The cavity has a shell. The shell has a sharp boundary. Along the boundary, thin scallops form. The scallops are density ripples. The burst exits through the cavity. It grazes the shell on some repeats. It avoids it on others. The result is a slight change in dispersion. The route outside remains similar. The route inside is variable. A payoff follows. Repetition allows subtraction. Features that remain constant across repeats are likely from the long path. Features that change are likely local. This turns one burst into a baseline. It turns the next burst into a deviation. A sequence becomes a diagnostic. The diagnostic is calm and incremental. It does not demand a single perfect observation. Another checkpoint appears. Repetition also tightens localization. Multiple bursts allow repeated timing comparisons. Each burst adds another constraint. The sky region shrinks as constraints accumulate. A single burst can paint a long arc. Repeated bursts can overlap arcs and reduce the area. The improvement is gradual. It resembles tracing a shape with many light strokes until the outline becomes clear. A single number sets the scale in a gentle way. A repeating source can be observed over about 1 year. That is like watching a slow season pass. Over that span, the long route is stable. The local environment can drift. The burst sequence becomes a record of drift. The scale shift is steady. The pulse itself lasts a millisecond. The monitoring spans months. The implied source distance can span billions of years in light travel. The contrast remains soft and clear. Another payoff appears. If the dispersion and scattering vary together, the same local structure may be responsible. A denser patch can both delay the pulse and scatter it. If dispersion varies while scattering stays stable, the patch may be smooth. A smooth gradient delays without roughening. This distinction is physical. It links timing to texture. A slow visual returns to texture. A thin sheet of plasma slides across a darker void. The sheet has a gradient. It is thicker toward one edge. The edge is smooth. The burst passing through shows a changing delay. The pulse remains sharp. The lack of extra tail suggests the sheet is not turbulent on small scales. Another sheet appears later. This second sheet is grainy. It has clumps. The delay changes again. The tail lengthens. The difference between sheets becomes audible in the pulse shape. Another checkpoint moves toward the engine question without rushing. Repetition constrains the source mechanism. A one-time catastrophe cannot repeat. A repeating source suggests a persistent object. It suggests an engine that can recharge. It suggests a setting that survives its own emission. This does not name the engine. It trims the list of plausible models. The limit of observation appears here with clarity. Even with repetition, the engine is inferred indirectly. The pulses may be sporadic. The intervals may not form a stable period. Without a clear rhythm, a rotation or orbit cannot be confirmed. The lack of a period is not proof of absence. It can arise from missing pulses. It can arise from drift in emission phase. It can arise from propagation effects that hide some bursts. The observation is incomplete sampling. The limit is practical and fundamental. The sequence is seen only when bursts occur. Silence may mean no emission. Silence may mean undetected emission. The distinction cannot always be made. Another payoff grows from this limit. Even without a period repetition still maps environment. The environment imprint does not require regular timing. It requires only comparison. The path effects reveal local plasma motion. The motion can be driven by winds of charged particles. It can be driven by expanding shells. It can be driven by turbulence in a surrounding nebula. These processes can change on human timescales. The burst offers a rare chance to sense such changes far away without direct imaging. The imagery softens toward a wider view. The repeating source sits within a faint host region. The region has a mottled glow. It has darker lanes. It has curved edges that hint at shells. The bursts are brief sparks within that quiet structure. Each spark carries a slight change. Each change points back to the same local neighborhood. The transition becomes gentle. With repetition, the next step is to look for signatures beyond timing and broadening. Subtle rotation of polarization can reveal magnetized plasma. That shift can add another layer of constraint without changing the calm pace. A burst can carry an invisible twist that survives the whole journey. That twist reveals magnetized plasma because the wave's orientation rotates as it passes through it. Light behaves as a traveling vibration. Even in radio, the vibration has a preferred plane at any moment. That preference is polarization. Polarization is the wave's direction of vibration. A burst can be strongly polarized at birth. It can also become polarized by passage. The key is change. When polarized radio crosses a magnetized plasma, the plane rotates. This is Faraday rotation. Faraday rotation is polarization turning in magnetized plasma. The turning depends on wavelength. Longer wavelengths turn more. Shorter wavelengths turn less. The burst then carries a frequency-dependent twist. The twist is not seen as brightness. It is seen as orientation. A calm visual anchor forms. A long filament of ionized gas hangs across a dark gulf. The filament has a brighter core. It has a softer outer sheath. Along its length, a faint magnetic ordering threads through like a lined grain. The burst crosses the filament. The pulse remains a short spike. Its orientation turns gradually with frequency. The turning is smooth. It resembles a ribbon that has been gently rolled between fingers. A small payoff arrives. Dispersion counts electrons. Faraday rotation links electrons to magnetic field. The combination separates two kinds of information. Dispersion alone cannot reveal magnetism. Rotation alone cannot reveal total electrons without ambiguity. Together they suggest how strong the magnetic influence is along the path. This matters because magnetism shapes plasma behavior. It guides charged particles. It supports waves and instabilities. It can organize turbulence or break it. A second checkpoint follows. Rotation can be huge near a dense magnetized region. It can be modest across diffuse intergalactic space. A burst that shows strong rotation likely passes close to a strongly magnetized environment. This points back toward the neighborhood of the source. It also points toward any compact magnetized screens along the way. The route is narrowed. The mystery becomes more structured. A single number holds the scale in a safe way. The rotation can be about 1,000 turns across the observing band. That is like twisting a rope around a hand many times. The number is large. The effect can still be measured because the turning follows a smooth rule with wavelength. A burst can be short. The twist can be deep. The scale shift is gentle. A millisecond event picks up a signature from fields that have been arranged over thousands of years. The arrangement may extend across light years. It may be confined to a thin shell near the source. The pulse becomes a messenger of both extremes. Another visual anchor appears within the filament. The filament edge forms a sharp boundary. Inside the boundary, the density is higher. Outside, it falls into a faint halo. The magnetic ordering changes across the boundary. The polarization rotation changes more quickly there. The boundary becomes visible through the twist. A small payoff follows. A sudden change in rotation with time suggests the burst passes through a moving or evolving magnetized screen. Repeating bursts contest this. If rotation varies between repeats, the magnetized region is likely local and dynamic. If rotation stays stable, the dominant contribution may be distant and steady. The twist becomes a time series of magnetism. The story stays calm. A signal would cross many plasma layers. Some layers carry little magnetic ordering. Some carry strong ordering. The strongest layers dominate the rotation. This is an important detail. Rotation is weighted by both density and magnetic field along the line. A weak field over a long path can matter. A strong field over a short path can matter more. The pulse does not label which is which. It provides the integral. Another payoff arrives. When rotation is extreme while dispersion is not extreme, the magnetic field influence per electron is high. This favors a compact, strongly magnetized region. When rotation is modest while dispersion is large, the path may be long and weakly magnetized on average. These are not final answers. They are consistent pictures. The visual field widens. A faint layered halo surrounds a galaxy. The halo is not uniform. It has shells and arcs. The arcs are density enhancements. Between arcs, the density falls. A magnetic field threads through in a softer way. The burst crosses the halo. The dispersion grows. The rotation grows modestly. The combination suggests a widespread contribution. Another checkpoint appears. Polarization itself can change within the burst. The orientation can swing during the millisecond. The swing can be smooth. It can be abrupt. A smooth swing suggests ordered emission geometry at the source. An abrupt swing can suggest multiple components or a changing propagation screen. This is subtle. It is also powerful. It adds a layer beyond timing. Another visual arrives. The burst emerges from a cavity. The cavity has a layered rim. The rim casts a shadow in density. The interior is cleaner. The wavefront leaves the cavity with a stable polarization angle. As it grazes the rim, the angle begins to rotate more rapidly. The rim behaves like a thin rotating lens. The pulse remains short. The angle shifts across the band. A small payoff follows. A burst that stays strongly polarized after traveling through the cosmos suggests the path does not fully randomize orientation. This implies the scattering is not completely depolarizing. The medium may be structured rather than chaotic. Or the scattering occurs in a way that preserves coherence. This narrows the kind of turbulence involved. The limit of observation arrives softly and specifically. Polarization is hard to interpret without full band coverage. If only part of the band is available, many rotations can wrap around and appear smaller. The measured angle is ambiguous by whole turns. The true rotation can be undercounted. Noise can also mimic small swings. Scattering can mix polarization states. Even when the rotation law is clear, separating source swings from propagation swings requires modeling. The observation measures only the final polarization as a function of frequency and time. It does not reveal the magnetic field map directly. This is the limit. It is not a defeat. It sets a boundary for certainty. Another payoff grows from staying within that boundary. A consistent rotation law across frequency is a strong sign of magnetized plasma. It anchors the interpretation. It also links the burst to environments where magnetic fields are coherent. The story begins to lean towards source hypotheses. Strong local rotation suggests a dense magnetized neighborhood near the engine. Weak rotation suggests a calmer surrounding. The transition is gentle. The next step turns from magnetism along the path to magnetism at the source. The same twist that survives the journey begins to hint at what kind of compact engine can create such ordered emission. A burst can seem simple until the path bends it into near copies of itself. A small detour by gravity or plasma can split one flash into several arrivals, which tightens constraints on distance and structure. In that region between source and arrival, space is not perfectly flat. Mass curves the route of light. Dense plasma can refract it as well. Either process can act as a lens. Lensing is path bending that creates multiple arrival routes. The routes differ in length. They also differ in how they pass through plasma. The result can be a burst that arrives twice or more. The copies can be close in time. The copies can be faintly different in shape. The physical detail is geometric. Each copy is the same wavefront. Each copy is sampled along a different corridor through space. A calm visual anchor forms. A dark compact mass sits in front of a faint glow. Around it a thin ring of light appears. The ring is not a solid object. It is the bending of paths into a circle. The ring has brighter arcs. It has dimmer gaps. A pulse travels behind the mass. The ring briefly brightens along one arc. A moment later another arc brightens. The pulse appears as two arrivals separated by a pause. A small payoff arrives. Two arrivals imply two distinct path lengths. The difference in arrival time reveals a characteristic lens scale. The lens can be gravitational. It can be plasma. The timing alone does not identify which. The shape of the copies helps. A gravitational lens tends to preserve the burst shape. A plasma lens can add extra dispersion and scattering on one copy. The difference between copies becomes diagnostic. The concept stays limited. Only 2 or 3 ideas matter. The first is lensing geometry. The second is time delay. The third is differential propagation through plasma. A single number holds the scale softly. The separation can be about 10 milliseconds. That is like the time between 2 gentle taps on a table. The original burst remains about 1 millisecond. This contrast explains why copies are visible. The delay is longer than the burst. The arrivals do not overlap. The pause can be measured cleanly. Another visual scene follows with slow clarity. A thin sheet of plasma drifts across a line of sight. The sheet has a curved edge. Its density rises smoothly toward the center. This makes it act like a refractive lens. The wavefront enters. One part of the wavefront is bent inward. Another part is bent less. 2 corridors form. One corridor passes through the denser center. The other skirts the edge. The denser corridor delays lower frequencies more. The pulse copy from that corridor arrives later. It also arrives more dispersed. The other copy arrives earlier. It stays cleaner. A small payoff settles in. If 2 copies have different dispersion, then part of the dispersion is local to the lens. This subtracts uncertainty from the long path. It separates intergalactic delay from a nearby screen delay. The burst becomes a layered probe. It is not only telling where electrons are, it is telling where a lens sits along the route. Another checkpoint appears, Lenses can magnify. A burst that is usually faint can become bright. This does not change the engine, it changes visibility. The observed population of bursts can be biased by lensing. Some bursts may be common but unseen. Lensing lifts a few above the threshold. This matters for understanding how many sources exist. Another payoff appears. A burst that is lensed is not necessarily intrinsically extreme. It may only be amplified. This reduces the pressure on models that require enormous energies. It also introduces new uncertainty. Without recognizing lensing, energy estimates can be too high. A calm visual anchor returns to the ring idea but shifts detail. The ring becomes an arc. The arc has a sharp inner boundary. It has a softer outer fall-off. The pulse brightens the arc briefly. The brightness is not uniform. It flickers along the arc due to small plasma irregularities. The flicker adds a faint tail on one copy. The other copy stays crisp. This combination shows how gravity and plasma can work together. Gravity bends the path into multiple images. Plasma adds texture and extra delay within each image. The scale shift remains gentle. A lens may be a compact object or a plasma structure only light years across. The effect is seen across distances of millions or billions of light years. A millisecond burst becomes a tool to detect a lens that cannot be seen directly. The event is brief. The inference spans cosmic space. Another checkpoint moves toward limits. Lensing models require assumptions about the lens shape. A simple lens can be approximated as smooth and symmetric. Real plasma lenses can be irregular. Real mass distributions can be clumpy. Multiple lenses can sit along one line of sight. The observed pattern of copies can then be complex. The limit of observation is specific. A single burst with two copies does not uniquely determine lens distance. Different combinations of lens mass and placement can produce similar delays. This is a degeneracy of modelling. Without additional events, the lens parameters remain uncertain. Even with repetitions, sampling is sparse. The burst may not recur in a way that maps the lens fully. The measurement is of time offsets and relative brightness. It is not a direct image of the lens. Another payoff grows from accepting this limit. Even when lens distance is uncertain, the mere presence of lensing proves that structure exists along the route. It proves that plasma can form coherent refractive features. It proves that gravitational curvature can create multiple paths detectable in time. This strengthens the picture of a textured universe. The burst is not only a messenger from a source, it is a scanner of what lies between. Another visual arrives to hold the calm. A broad filament crosses a void. Embedded within it is a denser knot with a rounded outline. The knot casts a faint shadow in intensity at some frequencies. The pulse crosses. A first copy arrives. A second copy arrives with slightly more smearing. The knot is not seen as an object. It is seen as a difference between copies. Another payoff follows. The difference between copies can reveal where scattering occurs. If only one copy is broadened, scattering is localized in one corridor. If both are broadened, similarly scattering is elsewhere. This distinction narrows the distribution of turbulence. The narrative prepares a soft transition. Lensing and polarization together can be especially revealing. A magnetized plasma lens can rotate polarization differently in each copy. That comparison can isolate magnetic structure. The next step moves gently from bending paths to measuring twists between paths. The pace stays quiet and steady. Two bursts can share the same sky position and still disagree in their hidden twists. That disagreement can isolate a magnetized lens because each path samples a different slice of the same field. At this distance, the earlier idea of multiple paths returns with a new layer. Lensing splits one pulse into copies. Polarization records orientation. Faraday rotation turns that orientation in magnetized plasma. When lensing creates two corridors, each corridor can rotate polarization differently. The difference becomes a clean comparison. It does not require knowing the absolute field. It requires only contrast between paths. A calm visual anchor forms. A dark mass sits before a faint glow. Around it a partial ring appears. The ring has a sharper inner edge. It has a softer outer fall-off. A pulse crosses behind. One arc brightens first, another arc brightens later. The two arrivals have nearly the same shape. Their polarization angles are not the same. One copy carries a gentle twist across frequency. The other carries a stronger twist. The difference is the clue. A small payoff arrives. If two copies differ in rotation while sharing the same long route, the magnetized region that matters sits close to the lens. The intergalactic path is common to both. It cancels out in the comparison. What remains is local. This tightens the search for where magnetism is concentrated. It turns a large unknown into a smaller zone. The journey moves toward the idea of differential rotation. Differential rotation is the rotation difference between two paths. It can be large even when the total rotation is uncertain. It can be stable even when the absolute angle wraps by many turns. This is useful. It avoids some ambiguities that plague single-path measurements. Another calm analogy supports the idea. It resembles two strings drawn across the same wet paint. Both strings start clean. One string drags through a thicker streak. That string picks up more colour. The other stays lighter. The difference reveals where the paint is thickest. The burst copies act like those strings. The paint is magnetized plasma. A small payoff follows. With two paths, even a complex medium can be sampled in stereo. The stereo does not make a full image. It does identify gradients across the lens. A gradient in rotation implies a gradient in magnetic field, strength, or electron density. The physical detail becomes more concrete. A plasma lens can have a core and an edge. The core is denser. The edge is thinner. The magnetic field can be stronger in the core. It can also reverse direction across the lens. Reversals matter. They can reduce net rotation along some paths. They can increase it along others. The two copies then disagree in a structured way. Another visual anchor arrives with slow pacing. A thin plasma sheet floats like a curved glass pane. Its center is thicker. Its boundary is sharp. Along the boundary, scalloped ripples appear. Within the sheet, faint magnetic ordering runs in parallel strands. The pulse enters. One corridor crosses near the center. The other corridor skirts the boundary. The central corridor produces more dispersion. It also produces more rotation. The boundary corridor produces less of both. A small payoff settles in. When rotation and dispersion rise together in one copy, the lens is likely both dense and magnetized. When rotation changes without a matching dispersion, change the magnetic field. Strength changes without much density change. This separates two factors that are otherwise tangled. The burst becomes a quiet test of magnetized structure. A single number holds scale in a safe way. The two copies can be separated by about 10 milliseconds. That is like the pause between two soft drum beats. The separation is long compared with the burst width. This prevents overlap. It allows the two polarization states to be compared cleanly. The scale shift remains gentle. A millisecond flash becomes a tool for sensing fields arranged over light years. The lens itself may drift over months. The field structure may evolve over years. The burst copies can appear in one moment. The inference reaches across long times. Another checkpoint appears. Multiple copies can also differ in scattering. A more turbulent corridor can smear the pulse and depolarize it. A less turbulent corridor can preserve sharpness and polarization. This difference can identify where turbulence sits in relation to the lens. If only one copy is smeared, the roughness is localized. If both are smeared similarly, the roughness lies elsewhere along the shared route. Another payoff appears. When polarization is preserved in a smeared copy, scattering is not fully randomizing orientation. This suggests coherent patches rather than chaotic mixing. When polarization is lost in the smeared copy, the corridor likely crosses more disordered plasma. The burst copies act like two threads through different fabric weaves. One weave is smooth, the other is coarse. The difference is felt in time and in orientation. The limit of observation arrives softly and specifically. The number of copies can be small. 2 copies give only one difference. Many lens models can produce the same difference. A plasma lens can be irregular. A gravitational lens can be accompanied by plasma screens. The measured differential rotation is an integral along each path. It does not reveal the precise field distribution. Even if the difference is large, the field could be strong in a tiny region, or moderate across a longer segment. Without additional events, the geometry remains underconstrained. Another limit appears. If polarization angles wrap by many turns across frequency, incomplete frequency, coverage can hide the true amount of rotation. The difference between copies can also wrap. Noise can blur angle estimates. Scattering can mix polarization states. The observation measures final orientation. It does not reveal the field direction uniquely. These boundaries remain. Another payoff grows from those boundaries. Even an imperfect differential measurement can still prove that the lens is magnetized. It can also show that magnetism varies across the lens. Variation implies structure. Structure implies a local environment that is not uniform. This helps distinguish between a purely gravitational lens and a plasma-dominated lens. It also points toward environments near compact engines where magnetized plasma can be dense and organized. The imagery slows into a wider view. A faint arc of lensed light lies on a dark background. Along the arc, the polarization twist changes slightly from one segment to another. The arc becomes a map of magnetism traced by a transient flash. The map is incomplete. It is still real. The transition is gentle. Once magnetism and lensing are considered together, attention naturally returns to the source neighborhood. The next step moves from path diagnostics toward plausible engines that can sit inside such dense and magnetized surroundings. A burst can sound like a single note, yet its surroundings can be inferred from how that note is shaped. The most plausible engines are compact and strongly magnetized because a millisecond flash requires a small region and an ordered field. At this distance, the story turns from path effects to source neighborhood. The earlier clues remain. The duration limits size. The polarization twist hints at magnetized plasma. Repetition hints at survival and recharge. These clues do not identify a single engine. They narrow the landscape. A calm visual anchor forms near the source region without naming it. A dense cavity sits inside a broader nebular glow. The cavity has a boundary like a thin shell. The shell is brighter along one arc. The arc suggests a compressed layer of plasma. Inside, the density is lower. Outside, the density rises into clumps. A burst appears as a thin seam. It leaves the cavity through a narrow channel. The channel has a sharp edge. The seam remains brief. The channel imprints extra rotation and scattering. A small payoff arrives. A compact engine can hide inside an extended environment. The environment can dominate propagation signatures. A strong rotation measure can come from the shell rather than the engine itself. This explains why different bursts from similar engines can look different. It also explains why the same engine can look different over time. The environment drifts. The engine remains compact. The next checkpoint introduces magnetosphere without heavy weight. A magnetosphere is a region shaped by a strong magnetic field. In a compact source, a magnetosphere can be dense with plasma. It can guide charged particles along curved lines. It can support sudden reconfigurations. Those reconfigurations can release energy in a brief radio flash. The physical detail matters. Field lines curve and converge. Plasma density can form layered surfaces around them. A burst that escapes may do so along a narrow beam. The beam can rotate in orientation within the millisecond. This can create a polarization swing. A small payoff settles in. A strong and orderly polarization suggests that emission is coherent and structured. It suggests a source region where motion is guided rather than random. This makes disordered thermal emission unlikely. It favors mechanisms that can align phases across a region. The story remains calm. The focus is not on drama, it is on constraints. The scale shift continues gently. The emission region can be smaller than a continent. The surrounding nebula can be light years across. The host galaxy can be tens of thousands of light years across. The path to arrival can span billions of light years. The burst links all of these scales in one brief event. Another visual anchor arrives distinct and slow. A thin torus of plasma circles an unseen compact center. The torus has a darker interior. It has a brighter rim where density rises. The rim is scalloped. The scallops are turbulence. The burst threads the torus edge. One burst leaves cleanly. Another grazes the rim and gains a longer tail. Repetition becomes a diagnostic of the torus structure. A payoff follows. A repeating source with variable scattering suggests a moving screen close to the engine. A torus or shell provides such a screen. As it drifts or expands, the line of sight changes. The burst becomes a probe of a small neighborhood that cannot be imaged directly. Another checkpoint introduces energy storage without overstating. A compact magnetized object can store energy in its magnetic field. The field can be twisted by motion in the surrounding plasma. When the twist becomes too strong, it can relax suddenly. The relaxation can accelerate particles. It can produce coherent radio emission. This is plausible. It is not proven. It matches the need for short timescales. It also matches the need for strong magnetism, indicated by rotation measures in some cases. A single number holds scale safely. The energy release can occur over about 1 millisecond. That is like a camera flash in time. The environment response can unfold over years. That is like slow weather compared with a lightning flicker. This contrast explains why repetition can exist. The engine can reset quickly. The environment evolves slowly. Another visual anchor slows the pacing again. A stratified shell expands outward. The shell has layers like thin smoke rings. Each layer has a slight density gradient. The burst passes through. The dispersion changes a little. The rotation changes more. The shell acts like a rotating lens. The differences between bursts become a record of shell expansion. A payoff follows. If rotation declines over time while dispersion stays similar, the magnetic ordering in the shell may be weakening as it expands. If both decline, the shell may be thinning. These trends would connect the burst to an evolving magnetized nebula. The narrative remains within constraints. It does not name a single object type as fact. It stays with plausible classes. Another checkpoint considers non-repeating bursts. A one-time burst could be produced by a catastrophic event. Such an event would not repeat. This could explain some observations. It is limited by uncertainty in sampling. A source could repeat but be missed. Silence is not proof. This is the limit of inference from sparse data. The limit of observation arrives clearly. Bursts are seen only when they occur. Their spectra can be patchy. Their polarization can be incomplete across frequency. Their time profiles can be altered by the medium. These constraints mean that engine models are judged on partial evidence. Many different engines can fit the same observed features. The evidence is indirect. It is filtered by propagation. It is also filtered by selection bias. Bright or lensed bursts are easier to detect. Subtle ones may be absent from samples. Another payoff grows from this limitation. Even when engines remain ambiguous, the allowed set becomes smaller as more channels are combined. Duration constrains size. Repetition constrains survival. Rotation constrains magnetism. Localization constrains environment class. Lensing constrains intervening structure. Each channel removes some possibilities. The mystery becomes a bounded space rather than an open fog. The imagery softens toward a wider view. The compact engine sits unseen. Around it, a magnetized cavity glows faintly. Beyond that, the host region blends into broader galactic structure. The burst is a small seam that appears and vanishes. The seam is short. The consequences for inference are long. The transition turns gentle. The next step moves from source hypotheses to how host environments bias what is seen. The same kind of engine can appear different in different regions. The narrative shifts outward to the habitats that surround these brief flashes. A burst can be born in one environment and transformed by another before it ever reaches open space. Host conditions often explain why similar engines produce very different signatures across the sky. At this distance, an origin is never just a point. It is embedded in gas dust and magnetic structure. The host region sets an initial filter. That filter can add dispersion, it can add scattering, it can add rotation, it can also add absorption that hides parts of the band. The burst that escapes is already shaped. The later intergalactic journey adds more. The result is a layered imprint. A calm visual anchor forms. A faint host region glows like a soft cloud. Dark lanes cut through it. Along one lane a thin shell arcs outward. The shell has a sharp rim. The rim is brighter on one side. The brightness suggests compression. Inside the shell the gas is warmer and thinner. Outside it is cooler and clumpier. A burst rises from within. It passes through the shell. The leading edge stays crisp. The tail lengthens slightly. The polarization twist strengthens. The burst becomes a messenger of the shell. A small payoff arrives. A strong rotation measure can come from a compact magnetized layer near the source. This means extreme magnetism along the path does not require the entire universe to be extreme. It can be local. The same is true for scattering. A turbulent pocket near the source can dominate broadening. A smooth intergalactic path can then contribute little. This helps explain diversity. Two bursts at similar distances can look very different if their local neighborhoods differ. The story moves through a gentle checkpoint. Host environments can be dense or diffuse. A dense host region adds more free electrons. That increases dispersion. It can also create a plasma frequency cutoff that weakens lower bands. A diffuse host adds less. The burst then arrives with a simpler spectrum. These differences matter for inferred distances. If host dispersion is large but assigned to intergalactic space distance can be overestimated. If host dispersion is small but assumed large distance can be underestimated. Host knowledge corrects the scale. A calm analogy supports the idea. It resembles a letter sealed in a scented envelope. The scent is not the letter. It is the packaging. The scent can be strong or faint. The letter can be the same in both cases. The burst is the letter. The host environment is the envelope. A small payoff follows. Recognizing the envelope prevents misreading the letter. The burst duration constrains the engine size. The host imprint constrains the neighborhood. Keeping these separate improves source hypotheses. The visual field shifts to another host scene. A spiral arm holds layered clouds. Some layers are ionized on their surfaces. The ionized surfaces form thin skins. Those skins have gradients. They also have small ripples from turbulence. A burst crossing the arm gains a long scattering tail. The tail is smooth and one-sided. The same burst crossing a halo instead would gain less. This reveals a practical clue. Strong scattering suggests passage through dense and turbulent regions. Weak scattering suggests passage through cleaner corridors. A small payoff appears. Host scattering can explain why some bursts show broad tails even when their dispersion is moderate. The turbulence can be intense in a small region. The integrated electron count can still be modest. This separates roughness from total content. It also points towards shells, bubbles, and filaments close to the source. Another checkpoint introduces absorption without clutter. Some host regions contain cold, dense gas. That gas can absorb or scatter low-frequency radio more strongly. The burst spectrum then appears patchy. It can show bright islands separated by quiet gaps. This patchiness is not always intrinsic. It can be a filter imposed by the host. A slow visual anchor holds the idea. A dark cold cloud sits like a wedge. Its edge is sharp. A thin, ionized layer wraps its surface. The burst passes behind. Only a slice of the band escapes cleanly. The rest is dimmed. The escaping slice arrives bright and narrow. Another payoff follows. Band-limited visibility can bias detection. Bursts that emit broadly may be seen narrowly if the host filters them. Bursts that emit narrowly may be missed if the filter blocks their narrow band. The observed population becomes shaped by host conditions. This is a quiet selection effect. It does not require any changes in engines. The scale shift stays gentle. The host region can be a few light years across. The host galaxy can be tens of thousands of light years across. The intergalactic journey can span billions of years in light travel. A millisecond event carries the imprint of the smallest region. It also integrates the largest. Host imprint sits at the inner boundary of that integration. Another visual anchor shifts to a calmer environment. A faint halo surrounds a host galaxy. The halo has layered arcs. The arcs are density enhancements. Between arcs, the density is lower. A burst exiting through the halo gains a smooth dispersion contribution. It gains little scattering. Its polarization twist is modest and stable. This suggests a cleaner passage. Another payoff appears. Host halos can contribute significant dispersion without adding strong scattering. This can reconcile bursts with high dispersion and sharp profiles. It also provides a consistent picture for bursts that seem distant but remain crisp. The limit of observation arrives softly and specifically. Host environments are often inferred from localization and from propagation signatures. Without a precise location, host attribution is uncertain. A burst seen only once cannot reveal which part of the host dominates its imprint. A repeating burst can help. Even then, changes can be due to moving screens rather than engine changes. Models can fit multiple host configurations. The data is filtered. It is indirect. It is also incomplete in frequency. This is a boundary in inference. It does not erase progress. Another payoff grows from that boundary. Host modeling can be tested statistically. If many localized bursts cluster in certain host environments, the link strengthens. If bursts show systematic relations between dispersion and rotation, host magnetism can be mapped in aggregate. The focus shifts from single events to populations. The imagery widens. Many faint host regions scatter across a cosmic web. Each has halos and arms. Each has shells and filaments. Bursts appear as brief seams. Some seams are heavily filtered. Some remain clean. The differences no longer feel mysterious in the same way. They feel like environment labels. The transition is gentle. After host effects are understood, attention naturally moves to cosmic consequences. The same dispersion that once hinted at distance can also reveal the distribution of ionized matter between galaxies. The narrative begins to lift from local envelopes to the larger web. A burst can act like a tally mark for matter that rarely shines. Dispersion across many bursts becomes a map of ionized gas in the cosmic web, even when that gas stays nearly invisible. At this distance, the story widens beyond single sources. Each pulse carries an integrated delay. That delay reflects free electrons along the line. When many localized bursts are compared, the delay can be partitioned. Part belongs to the host, part belongs to the near environment, part belongs to the space between galaxies. That middle part is the quiet prize. It traces diffuse ionized gas that is hard to detect otherwise. A calm visual anchor forms. A vast web stretches across darkness. Thin filaments connect brighter nodes. Between filaments lie wide voids. The filaments are not solid lines. They are gradients. Their edges fade. Their centers are denser. A burst crosses a filament. The pulse becomes slightly more delayed than a similar burst that crosses a void. The difference is not a bright flash. It is a gentle shift in arrival timing across frequency. A small payoff arrives. A single burst cannot reveal where the electrons sit. A collection of bursts can reveal average electron content as a function of distance. This is because different lines of sight sample different parts of the web. Over many events, patterns emerge. Lines that cross filaments tend to have higher dispersion than lines that cross voids. The dispersion becomes a statistical tracer of structure. The journey moves into the idea of baryon census without heavy weight. Much ordinary matter is ionized and diffuse. It does not glow strongly. It does not form bright clouds in most places, yet it must exist. Dispersion provides a way to count it indirectly. The count is not perfect. It is still meaningful. A calm analogy supports the idea. It resembles weighing fog by how much it slows a passing beam. The fog is unseen from far away. The delay of the beam reveals that it is there. A small payoff follows. If the average dispersion rises with distance in a predictable way, the average density of ionized gas can be inferred. Deviations from that rise indicate over-dense or under-dense routes. The bursts become probes of the cosmic web itself. The physical detail stays grounded. Filaments have cores and outskirts. The electron density changes with radius. This creates gradients in dispersion contribution. A burst passing near a filament core receives more delay. A burst passing along the outskirts receives less. The dispersion is an integral. It cannot show the cross-section directly. With many lines, the cross-section can be inferred statistically. Another visual anchor arrives with slow clarity. A filament is seen in silhouette against a faint glow. Its core is a narrow ridge. Around the ridge is a softer halo. Small knots are embedded along it. Each knot is a place where density rises. The burst crosses near a knot. The dispersion is higher. The pulse may also gain a little scattering if turbulence is present. Another burst crosses a smoother part of the filament. The dispersion is still higher than void, but scattering remains small. A small payoff settles in. Dispersion and scattering do not have to track together. A filament can be dense but smooth. It can add delay without smearing. This distinction helps separate density from turbulence. It prevents confusion between content and texture. Another checkpoint appears. To isolate intergalactic dispersion, host contributions must be estimated. Localization helps by identifying a host environment class. Repeating behavior can also hint at strong local screens. Rotation measures can indicate local magnetized plasma that might accompany dense electron screens. These auxiliary clues reduce host uncertainty. The remaining dispersion becomes a cleaner measure of intergalactic content. The scale shift is gentle and steady. A millisecond burst travels for billions of years. Over that time, the universe expands. Expansion stretches the wave. It also changes how electron density evolves with time. The dispersion relation with distance includes this evolution. The burst becomes a probe of cosmic history. It links present observations to conditions long ago. A single number sets scale safely. The travel time can be about 1 billion years. That is like a long geological age. The burst duration remains 1 millisecond. This contrast holds the narrative together. A tiny event can carry information across an age. Another visual anchor supports cosmic time. A filament is seen at 2 epochs. In the nearer epoch, it is thicker and more structured. In the earlier epoch, it is denser and more compact. A burst crossing the earlier filament picks up more delay per unit distance. This is because the universe is denser earlier. The pulse carries that density through dispersion. A payoff follows. If dispersion as a function of distance is measured across many sources, the average ionized density evolution can be tested. This is a way to study how matter distributes over time. It is calm and indirect. It does not require bright emission from the diffuse gas itself. The limit of observation arrives softly and specifically. Dispersion-distance relations rely on accurate distances. Distance estimates depend on localization and on association with a host region. Misidentification can bias results. Host contributions can also vary widely. A dense local screen can add large dispersion that masquerades as intergalactic content. Without reliable host subtraction, the inferred cosmic density can be skewed. There is also line-of-sight variance. Filaments and voids create scatter around the mean. A small sample can mislead. This is the boundary of statistical inference with limited events. Another payoff grows from acknowledging the boundary. Even with uncertainty, dispersion measurements can still bracket the allowed range of diffuse ionized matter. As samples grow, the mean becomes clearer. The scatter becomes a feature rather than a nuisance. The scatter maps the cosmic web's clumpiness. This turns variability into information. The imagery widens. Many bursts cross many routes. Some routes thread multiple filaments. Some pass through wide voids. The dispersion values spread into a distribution. The distribution has a center and a tail. The center reflects average density. The tail reflects dense crossings. The tail is not a mistake, it is structure. The transition becomes gentle. After density is traced, magnetism can be traced as well. Rotation measures across many lines of sight can map where magnetized plasma resides in the cosmic web. The next step moves from counting electrons to sensing fields on intergalactic scales. A burst can pass through empty-looking space and still reveal a faint magnetic skeleton. Rotation across many bursts can trace where intergalactic magnetism gathers, even when the field is too weak to glow. At this distance, magnetism is not treated as a decoration. It is a structural ingredient. It guides charged particles. It influences turbulence. It shapes how plasma evolves in filaments and halos. Faraday rotation offers an indirect sensing method. Rotation measure is the path-integrated magnetic influence. It combines electron density and the magnetic field along the line. It is a subtle quantity. It is also sensitive. The narrative stays calm. The goal is not a final map. The goal is a gradual constraint. A calm visual anchor forms. A long filament spans a void. Its core is slightly brighter. Its edge fades. Along the filament, faint strands run in parallel. The strands are not visible light. They are ordered magnetic regions, inferred from rotation. A burst crosses the filament. The polarization angle rotates with frequency. Another burst crosses a void. Its rotation is smaller. The difference is a quiet hint of where magnetized plasma resides. A small payoff arrives. If rotation tends to be larger along lines that also show higher dispersion, magnetism is likely concentrated where electrons are concentrated. This is expected in filaments and halos. If rotation does not track dispersion, magnetism may be patchy, or partly cancelled by reversals. This comparison matters. It tells whether the cosmic web has coherent fields or tangled ones. The journey moves through a checkpoint of reversals. Magnetic fields can change direction along the route. If the field reverses, contributions can cancel. Rotation then becomes smaller than expected from density alone. A line of sight can pass through several layers with alternating field directions. The net rotation can be modest even if local fields are strong. This makes interpretation delicate. It also makes differential comparisons valuable. A calm analogy supports the idea. It resembles walking on a shoreline with alternating currents. Some segments push in one direction, others push back. The net drift after a long walk can be small. The currents were still real. The cancellation hides them. Rotation behaves similarly. A small payoff follows. A modest rotation does not imply no magnetism. It can imply cancellation. This keeps conclusions cautious. It also motivates using many lines of sight. With many bursts, the distribution of rotation measures can be studied rather than single values. The distribution can reveal whether strong rotations are rare or common. Another visual anchor arrives with slow precision. A halo around a galaxy shows layered arcs. The arcs are density enhancements. Along some arcs, magnetized plasma is more ordered. Along others, it is more tangled. A burst passing near an ordered arc shows a steadier rotation law. Another burst passing through a tangled arc shows more variable polarization behavior. The physical details are layered. Boundaries matter, gradients matter. The burst is sensitive to these changes. A payoff appears. A stable rotation law suggests a coherent magnetized region along the path. A messy polarization pattern suggests mixing or rapid changes in field direction on small scales. This helps classify magnetized environments in a way that brightness cannot. Another checkpoint introduces cosmic scale gently. Intergalactic fields are often expected to be weak. Even a weak field can matter over long distances. Over millions of light-years, a tiny influence can accumulate. This is the essence of the method. A millisecond burst carries a record of that accumulation. The scale shift remains calm. A flash lasting a millisecond samples a path spanning billions of years in light travel. The field structure along that path evolves over cosmic time. The burst integrates it into a single number and a smooth frequency behavior. A single number holds scale safely. The polarization rotation can be about 10 turns across the observing band for some long paths. That is like slowly winding thread around a spool. It is not dramatic in itself. It is measurable because the rotation follows a systematic dependence on wavelength. Another visual anchor supports this gentle accumulation. A broad filament is seen as a faint gradient. Along its length, small knots appear. Each knot is denser. Each knot has its own magnetic patch. The burst passes through several knots. Each knot adds a small piece of rotation. Some pieces add, some subtract. The net is the final twist. The twist is a sum of quiet contributions. A payoff follows. By combining rotation with dispersion, a rough estimate of average magnetic influence per electron can be made. This does not yield a detailed field map. It does suggest whether the environment is strongly magnetized relative to its density. If rotation is high for a given dispersion, the magnetic field is more coherent or stronger. If rotation is low, either the field is weaker or cancellations are stronger. This helps distinguish magnetized halos from more weakly ordered filaments. The limit of observation arrives softly and specifically. Rotation measures of bursts include contributions from the near-source environment and the host halo. These can dominate. Without careful subtraction, intergalactic magnetism can be overestimated. The line of sight also includes the region near the arrival end, which can add its own rotation. Separating these layers requires assumptions. It requires statistical modeling. It requires many events. Even then, field reversals can hide strength. This is a fundamental degeneracy. The measurement is an integral. It does not show where along the path the rotation occurs. Another payoff grows from this boundary. Even if exact placement is uncertain, correlations still teach. If rotation tends to increase in directions where galaxy density is higher, intergalactic magnetism likely follows structure. If rotation shows little correlation, fields may be more uniform or more tangled. The method can constrain families of models rather than a single map. The imagery widens to a quiet panorama. Filaments connect clusters, halos overlap, voids expand between, bursts appear sporadically across the web. Each burst adds one more sample of magnetized plasma. The samples gradually fill in a statistical picture. The transition becomes gentle. After electrons and magnetism are traced, attention can shift to time. Some bursts originate from far epochs. Their paths sample earlier cosmic conditions. The next step moves toward how burst populations and distances can reveal cosmic evolution and the remaining mysteries that keep the field unsettled. Some signals arrive as if they come from the present, yet their paths cross eras that no longer exist. The combined pattern of dispersion and rotation across distance can reveal how ionized matter and magnetism change over cosmic time. At this distance, time is not an added detail. Time is embedded in every long path. A pulse that travels far leaves earlier epochs and enters later ones. The plasma it crosses is not constant. Density slowly declines as expansion stretches space. Structures mature as filaments thicken and halos grow. A burst samples that history in one brief sweep of frequency. A calm visual anchor forms. A long filament hangs between two dark voids. The filament is braided. Its core is a narrow ridge. Its outskirts fade into a soft haze. Along the ridge, knots sit like beads in a translucent thread. A burst crosses the filament at a far segment that belongs to an earlier epoch. The filament there is tighter. Its boundary is sharper. The same kind of path nearer in time crosses a filament that looks puffier and more relaxed. A small payoff arrives. Higher dispersion per unit distance at greater look-back time follows naturally from higher average density earlier. This turns dispersion into a quiet clock. The clock is not exact for one event. It becomes clearer across many events. Another checkpoint settles in. The observed dispersion for a given distance is not a single number. It is a spread. Some paths cut through multiple filaments. Some pass through wide voids. The spread itself contains structure information. If the spread narrows with time, the web becomes more uniform along typical lines. If it widens, dense structures become more contrasted against voids. A small payoff follows. The width of the dispersion distribution can trace the growth of cosmic clumpiness. This is a different measurement than the mean. It uses variability rather than averages. The imagery slows again. A broad void sits like a shallow bowl. Its interior is darker and cleaner. Its rim touches thin filaments. A burst path that stays in the void shows a smoother spectrum. Its arrival is sharper. A path that grazes the rim meets a gradient. The gradient adds a gentle extra delay. The delay changes more rapidly at lower frequencies. The pulse becomes slightly stretched. The physical detail is simple. A boundary between void and filament acts like a soft edge. A small payoff settles in. Boundaries contribute disproportionately because gradients concentrate change. This means a few crossings can dominate an otherwise quiet path. Time evolution then matters in how common such crossings are. As structures grow, boundaries occupy different fractions of typical routes. The narrative moves to the second concept. Selection bias shapes which bursts become part of the story. Only bursts that reach the arrival end are counted. Paths with extreme scattering can smear a pulse until it is hard to recognize. Paths with strong absorption can dim a broad band into a narrow sliver. This does not mean such paths are rare. It means they are underrepresented. A calm analogy supports this idea. It resembles sediment layers forming on a lake bed. Coarse grains settle quickly near the shore. Fine grains drift and settle farther out. The final layer pattern reflects both supply and filtering. The burst population reflects both engines and propagation filters. A small payoff arrives. A change in the observed population with distance does not automatically mean engines evolve. It can mean filters evolve. Early epochs can have denser environments. Denser environments can scatter more. More scattering can hide some bursts. The observed set then tilts toward cleaner corridors. This keeps conclusions cautious. Another visual anchor appears with slow clarity. A halo around a distant host region looks like a faint layered fog. The fog has a brighter inner band. It has a darker gap. It has an outer skirt that fades. A burst leaves from within. The inner band adds rotation. The outer skirt adds dispersion. The gap adds little. Over time, the halo expands. The bands drift outward. The same kind of burst later crosses a different band arrangement. A small payoff follows. If rotation measures decline with look-back time at fixed dispersion, field coherence may be changing. If rotation grows faster than dispersion, magnetism may be amplified in dense structures earlier. These are population-level statements. Single events cannot carry them alone. Another checkpoint arrives. Repeating sources add a special time marker. Repetition allows the environment near the source to be sampled more than once. This helps separate local evolution from distant evolution. If a repeating source shows slow drift in dispersion, while its distance is fixed, that drift is local. If many sources at different distances share a common trend, that trend can be cosmic. A small payoff settles in. Repetition acts like a control group. It does not remove all uncertainty. It does reduce confusion between local screens and intergalactic contributions. The scale shift remains gentle. A millisecond pulse is compared across a span of about 10 billion years, like the slow accumulation of layers into deep rock. The pulse stays brief. The history is vast. The method is to compare many brief events across that vastness. The imagery widens. A chain of filaments runs across the dark. Some segments are thin and taut. Some are thick and frayed. The frayed segments suggest turbulence and mixing. The taut segments suggest more ordered flow. A burst crossing a frayed segment gains a broader tail. A burst crossing a taut segment stays crisp. A small payoff appears. If scattering tails become more common, at greater look-back time earlier environments may be rougher on average. If tails do not change, roughness may be dominated by local source neighborhoods rather than cosmic conditions. The limit of observation arrives softly and specifically. Distances can be uncertain when host contributions to dispersion vary widely. Some sources carry heavy local screens that masquerade as long paths. Some long paths look modest if field reversals cancel rotation. The sample can also be incomplete. Extreme scattering can hide events at large distance. Patchy absorption can remove low-frequency information that would constrain dispersion and rotation laws. These limits mean time trends can be blurred or biased. Another payoff grows from those boundaries. The same limitations suggest robust strategies. Trends that appear in multiple independent measures are harder to fake. A joint trend in dispersion distributions, rotation distributions, and scattering prevalence is more convincing than any single channel. Cross-checks between repeating and non-repeating samples can also test for local contamination. The picture remains gradual. It is an accumulation of constraints rather than a single revelation. The final imagery softens. The cosmic web looks less like a static scaffold and more like a slow-breathing structure. Filaments thicken, voids widen, halos expand. Bursts appear as brief seams that stitch across epochs. The transition becomes gentle. The next step moves from time trends to consequences. As matter and magnetism are traced, the results inform how structures assemble and how environments shape what is seen. The narrative shifts toward the broader perspective that emerges from these constraints. A burst can appear to change character even when its source stays unchanged. Propagation can magnify or split the signal, shaping what is noticed and what is missed. At this distance, the mystery is partly about selection. Some paths make bursts easier to detect. Some paths hide them. The population that arrives is filtered by space itself. 3 concepts hold the section. Gravitational lensing bends paths through mass. Plasma lensing focuses waves through density gradients. Selection bias follows from both. A calm visual anchor forms. A distant galaxy halo lies between source and arrival. The halo is smooth at first glance. Its density fades outward in a gentle gradient. Closer in the gradient steepens. A thin arc of light would form around the halo if a steady glow sat behind it. For a burst, the halo makes something different. It creates multiple routes. Each route has a different path length. Each route bends around a different part of the halo. The burst arrives more than once. Each arrival is the same event. Each arrival is a different path imprint. A small payoff arrives. Multiple arrivals do not require multiple engines. They can come from one burst seen along several paths. This makes repetition in time ambiguous. A repeated pulse can be a true repeater. It can also be a lensed echo. The difference is subtle. The echo copies the spectrum structure more closely. The echo carries nearly the same internal pattern. The echo may differ mainly in brightness and slight smearing. The journey moves to a second visual anchor inside the same scene. Near the halo center, the bending is stronger. The roots approach a ring like geometry. A thin ring would be possible for a perfectly aligned background. For a burst, the ring becomes a set of discrete images. Each image has a distinct delay. One arrives first, another arrives later. The later one is dimmer. Its tail is slightly broader. The difference comes from a longer route through plasma. A single number sets scale safely. The delay can be about 1 day, like the slow spin of a large planet. The burst itself lasts a millisecond. The contrast between a millisecond and a day is quiet and striking. A small payoff follows. A long delay between echoes allows a separation between intrinsic variability and path variability. If two pulses share the same fine spectral pattern, lensing becomes plausible. If patterns differ, true repetition becomes more plausible. The section stays careful. Perfect copying is not guaranteed. Plasma along each route can modify the copies differently. This leads to the next concept. Plasma lensing is not mass lensing. It is refraction by electron density structure. A plasma lens can focus radio waves like a curved surface of density. The focusing is frequency dependent. Lower frequencies bend more. Higher frequencies bend less. The result can be bright bands. The result can also be deep fades. A calm analogy supports the idea. It resembles sunlight passing through rippled ice on a frozen pond. The light forms moving bright lines on the lake bed. The ripples do not create light, they redirect it. The burst is redirected in the same way. A small payoff arrives. Plasma lensing can make a burst seem stronger without changing the engine. It can also make a burst disappear at some frequencies. This produces apparent spectral islands. It can also produce bursts that appear clustered in time. As a lens drift's focusing can peak intermittently. The drift can create windows of visibility. The scene shifts to a slow and concrete plasma lens image. A dense sheet of ionized gas lies along the route. Its edge is sharp. The sheet is not uniform. It has folds. It has a wavy boundary. Along one fold, the density increases smoothly. The increase forms a lens-like ridge. A burst passes behind the ridge. The ridge focuses the wave. The pulse brightens. Its spectrum shows a narrow, bright stripe. Moments later, a neighbouring route passes through a defocusing region. The pulse dims. Its spectrum looks mottled. A small payoff follows. Focusing and defocusing can mimic intrinsic energy variation. A dim burst can be a strong burst seen through a defocusing patch. A bright burst can be a modest burst seen through a focusing ridge. This matters for population statistics. The observed brightness distribution is not only a property of engines, it is also a property of intervening structure. The section moves through another checkpoint that links the two lenses. Mass lensing creates multiple paths. Plasma lensing can act differently on each path. One lensed image can be focused, another can be defocused. The echoes can have different amplitudes. The echoes can show different fine structure. This makes classification challenging. A small payoff arrives. The combination of lensing types can explain why some repeating-like sequences do not match perfectly. The mass lens provides the duplication. The plasma provides the differences. The physics is layered. The pulse becomes a probe of both mass distribution and plasma structure. The scale shift remains gentle. A plasma lens can be small compared to a halo. It can be the size of a solar system or smaller. The halo can span tens of thousands of light years. Both can influence the same millisecond burst. Small structure shapes brightness. Large structure shapes path duplication. The burst carries both. A limit of observation arrives softly and specifically. Lensing inferences rely on recognizing patterns across time and frequency. Sparse sampling can miss echoes. If an echo arrives much later, it can be outside the monitoring window. If a plasma lens narrows the visible band, the copied pattern can be incomplete. If scattering smears one image, the match can be blurred. The result is degeneracy. A true repeater can resemble a lensed single burst. A lensed burst can resemble a complex engine. Without continuous coverage, separation is uncertain. Another payoff grows from that boundary. Even imperfect identification can still inform the population. Rare, strong lensing events constrain how often alignment occurs. Frequent plasma focusing episodes constrain how common sharp density gradients are. The distribution of observed brightness and widths carries information about lensing prevalence. The outliers become useful. They are not only noise, they point to extreme paths. The imagery widens to a calm panorama. Many lines of sight cross the cosmic web. Some pass near halos, some pass through voids, some skim sharp plasma sheets in filaments. Bursts appear unevenly across this landscape. The unevenness is not only where sources are, it is also where visibility is enhanced. This is selection bias in physical form. A final payoff settles in. The enduring mystery is shaped by two layers. There is uncertainty about engines. There is also uncertainty about filters. The filters can manufacture apparent complexity. The engines can still be complex. Untangling the two is the continuing task. The transition becomes gentle. After lensing and selection are acknowledged, the narrative can soften toward a stable view. The next section brings the pieces together. It holds the unknowns without tension. It settles into the quiet scale of a universe that carries millisecond signals across deep time. The final shape of the mystery is quieter than the first impression. A burst is brief, yet its path carries layered information that can be arranged into a stable picture. At this distance, the unknown remains, but the structure of the unknown becomes clearer. Three concepts close the arc. A unified propagation budget separates local and long-path effects. A population map uses many bursts to trace shared conditions. A residual mystery remains when propagation and statistics are accounted for. A calm visual anchor opens the section. A wide dark plane of space is crossed by faint threads. The threads are filaments. They curve gently. They intersect at thicker knots. Between them voids form smooth basins. Along one filament, a thin sheath of ionized gas wraps the denser core. The sheath has gradient. The core has a sharper ridge. A burst crosses the sheath first. It gains dispersion. It gains a small amount of scattering. It then crosses the ridge. It gains more. The ridge acts like a thin boundary layer. The boundary concentrates change. A small payoff settles in. A large fraction of the total imprint can come from a few narrow layers, not from the entire distance evenly. This explains why two similar distances can look different. It also explains why outliers exist. The journey moves to a quiet checkpoint. The propagation budget is a way to account for the imprint. It is not a single equation. It is a structured allocation. One part belongs near the source environment. One part belongs to the host halo and immediate surroundings. One part belongs to the intergalactic route through filaments and voids. Each part leaves signatures with different textures. Local screens can vary rapidly with repetition. Intergalactic contributions vary mainly with route geometry and distance. This separation is never perfect. It can still be improved by population behavior. A small payoff appears. Even when distances are uncertain, the joint behavior of dispersion, scattering, and polarization trends can narrow what is plausible. The picture becomes less about exact localization and more about consistent patterns across many events. The imagery shifts to a new slow scene. A long corridor through a void appears almost empty. The void has a subtle gradient. Its center is cleaner. Its edges are faintly hazy. A burst passing near the center arrives sharper. Its spectrum is smoother. Another burst that skirts the void boundary arrives with a softer tail. The tail is longer. The boundary shows as a mild frequency-dependent blur. A small payoff arrives. Void corridors are not simply low density. They are also low variability. They preserve sharpness. Filament edges are not simply denser. They are also more structured. They add variability. This turns the cosmic web into a lensing and scattering landscape without using any human artifact. A gentle scale shift follows. A millisecond pulse reflects conditions across billions of years of travel. The imprint is small in time. The cause is vast in space. Both can be held together without tension by treating the pulse as a probe rather than a message. Another checkpoint arrives. The population map is built from many bursts. Some are bright, some are faint, some repeat, some do not. When these are combined, the mean dispersion at a given distance becomes a baseline. The spread around that baseline becomes a tracer of route diversity. The prevalence of scattering tails becomes a tracer of fine structure. The behavior of polarization becomes a tracer of magnetic coherence and reversals along the path. A small payoff settles in. The mystery shifts from a single burst to the ensemble. The ensemble can reveal stable features even if each event is noisy. This is how uncertain engines can still produce useful cosmology. The visual anchor deepens. A thick knot at a filament intersection appears as layered mist. The knot has a brighter inner band. It has an outer skirt. Between them lies a subtle, shadowed gap where density drops. A burst that passes through the inner band emerges with a stronger rotation signature. A burst that passes through the outer skirt gains dispersion but less rotation. The gap produces a small relief in the imprint. This physical layering provides a concrete, repeatable pattern. A small payoff arrives. When dispersion and rotation do not track each other, layered environments provide a natural explanation. Density and field can be arranged differently in space. Field reversals can cancel rotation even when density remains high. This reduces the temptation to force a single, simple model onto all events. The limit of observation arrives softly and specifically. The greatest uncertainty is the hidden contribution close to the source. A dense local screen can mimic extra distance. A turbulent local region can add scattering that resembles filament structure. Polarization can be scrambled by small-scale magnetic tangles. If the source sits in a complex local environment, disentangling local and intergalactic parts becomes difficult. The second limitation is incompleteness. Events strongly scattered can be hard to recognize. Events strongly focused can be overrepresented. These biases can distort the population map. The third limitation is degeneracy. Different combinations of local screen and long path can produce similar observables. These limits are not failures. They're boundaries that define what questions are currently answerable. A small payoff rises from those boundaries. The constraints still narrow the space of possibilities. Some source hypotheses predict strong local variability. Some predict stable local contributions. Repeating behavior can test this. Some routes predict scattering that grows with distance. Some predict scattering dominated by local screens. Population trends can test this. Even when the exact engine remains unknown, the propagation picture becomes increasingly solid. The section turns toward a gentle settling. The remaining mystery is not an empty gap. It is a bounded region, with edges that are slowly sharpening. It contains engine physics that is still uncertain. It also contains propagation details that are becoming measurable. The cosmic web acts like a quiet archive. Each burst adds one more thread to the archive. The archive is not read all at once. It is read slowly through distributions and correlations. The final imagery softens into rest. The filaments remain suspended. The voids remain open and calm. The layered sheaths remain faintly luminous in imagination. A burst crosses and leaves a slight imprint. Then the darkness returns to stillness. The transition is gentle. The narrative can now remain in that stillness, carrying forward a stable sense of scale and a quiet acceptance of what remains unknown.